Right. Tonight we're going to try to solve this system of equations by using the substitution method. And when we solve this, we're going to get an ordered pair that satisfies both equations. And if we find an ordered pair that makes both equations true, we know we have our solution. So when I'm using the substitution method, and what makes substitution beneficial for this equation is I have a variable here, y, with a coefficient of 1. So it's fairly easy for me to solve for one of the variables or isolate one of the variables so I can find out what that variable equals. So here in my equation 3x plus y equals 9, I can isolate y fairly quickly just by subtracting the 3x and subtracting 3x from this side. And here, these cancel. I'm left with 0, and then 0 plus y is just y, and y equals 9 minus the 3x. Okay, I can't combine those because they're not like terms, so I just leave it, 9 minus the 3x. So we know what y equals. And now that I know what y equals, I can substitute it into my second equation. That's why they call it the substitution method, because I'm going to substitute the value of y into this equation, so I'm working with just a one variable equation. So here I have 2x plus my 3, but instead of writing the y, I'm going to write what y equals. So it's the 9 minus 3x, and that equals 13. So you can see we have just the one variable equation now, just our x's. So I want to simplify this left side of the equation fully by first distributing. Okay, so I'm going to have 2x plus 3 times 9, which is 27, minus the 3 times 3x, or 9x, and that equals 13. Next step, I see that I have multiple x's on the same side, so I can combine my like terms. And if I combine my like terms, I know a 2x minus 9x is just a negative 7x, or minus 7x, so I have 27 minus 7x, and that equals 13. And now it's a two-step equation. I can subtract 27 from both sides. Subtract 27. Again, here I get 0, and I'm left with a negative 7x, and that equals a negative 14. Okay, 13 take away the 27 gets me negative 14. And then if I divide by a negative 7 and divide by a negative 7, I get x equals, well, negative 14 divided by negative 7 is just 2. So I know my value of x, but to have an ordered pair, I know I need an xy coordinate. So to find the value of y, I take my new value of x that I have here, and I can substitute it back into one of my original equations. So I'm going to use the first one, and I'm going to substitute x with the value 2. So I have 3 times 2 plus y equals 9. Well, I know 3 times 2 is 6, plus y equals 9. And then if we solve for y, we can just subtract 6, and we get y equals 3. So my ordered pair that satisfies both equations is the ordered pair 2, 3. We can check this, and the check is really important because it lets you know, did we do it right? So if I do my check, I'm going to just use that ordered pair 2, 3 in both equations. So I'm going to write my first equation here, the 3x plus y equals 9. And my second equation, the 2x plus 3y equals 13. And I'm going to substitute 2, 3 into both. So where there's an x, I'm going to put a 2, and where there's a y, I'm going to put a 3. So I'm going to do 3 times 2 plus 3, and I'm checking to see, does that equal 9? Well, I know 3 times 2 is 6 plus 3, and that in fact does equal 9. We get 9 equals 9. So it works for that equation. The other equation, if I substitute in here, making some more room on my paper, again, I'm going to substitute again. Where there's an x, I'm going to put a 2. Where there's a 3, I'm going to substitute a 3. Excuse me, where there's a y, I'm going to substitute a 3. So I'm going to have 2 times 2 plus 3 times 3. I'm checking to see, does that equal 13? Well, 2 times 2 is 4, and 3 times 3 is 9, and 4 plus 9 does equal 13. So it is a solution for both. So I know that is our answer, the ordered pair 2, 3.